Hi everyone and welcome to a new video about power electronics. This is our example where we discuss some basic power calculations that we encounter in power electronics. We will see some examples and step by step the calculations for it and also verify these in MATLAB simulations. Okay, let's see what we will encounter in these series of examples. This is the content. We will see the average current, how we can calculate that, the average voltage, and also the observed power by the load elements. And we will see also how we can determine the RMS current and also the RMS voltage. It's also called the effective value. So let's see the first example and dive to it, and then we will build up, of course, the level. The first example is very straightforward. We have one source here, which is the pulse here, which is given by this shape, which is 10 volts between 0 and dt, and d here is the duty cycle, given here is 0.49 or 49%. It is 0 volts for the rest of the period, so in one period we have actually a part which is 10 volts, the other part is 0 volts. The load here is a pure resistor, and that has a value of 100 ohms. We measure the voltage between the resistor like so, and the current flowing here is also given. Now what we like to know is the average and the RMS value of this pulse waveform from this pulse waveform in this load. So let's try to discuss these four unknowns here. The solution, first the calculations, the average load voltage, VO, that is actually here between these two nodes, and that is calculated really straightforward by using the amplitude of this signal, which is then in this case 10 volts for this period, for this part of the period, times the duty cycle. So duty cycle times the amplitude of that source. That will give us 0.49 times 10, 4.9 volts. That's really that simple for this case. The average load current, IO, is also straightforward calculation. That is using Ohm's law. We already know from question A what the average load voltage is. So you divide by 100, which is the R, pure R. So you get now here 49 milliamps. The next one is the RMS load voltage. The RMS load voltage is then given by this expression in general, so we need to know what the output voltage expression is as a function of time. You square that, you integrate that from 0 to t, so the full period, and you divide by the period, and then you take the square root. That is root mean square. So you square it and you take the mean, that is the integration, and then divide by the period, and then you take the root. Okay, we know that our signal is VO here at the output, but if it is also equal to Vs, so we can say that is equal to each other, and we know that we can split our output voltage then in two parts, which is then a part that this is 10, which is then equal to Vs, and there's also a part which is 0. That's actually shown here, so the square root is then longer, and you have then this part which is then split in two, which is then 0 to dt, and then from dt to t, so in that first period or first part is 0 to dt, your VO or Vs, which is exactly the same, is 10. You square that, but for the second part it is just 0, and you square that. So officially I'm just making it really straightforward. We don't know what the period is, it's not given, so we just keep it as it is. Now what you have here is this part is 0, so that will go, and this is just 100, so what you get is actually here 100, and then since you integrate this, there will be then 100t, and you need to evaluate that between 0 and dt. Similar for the second part, but that will go for sure. And then what you have here is then 100 dt, and the square root of that 1 over t times this part. Now you see that the t here and t there will cancel each other out, so it doesn't matter what the period is actually, it's just about the duty cycle. Now what you have is then the following. Now the duty cycle, the t will go, that will be then 100 times 0.49 will be then square root of 49. Square root of 49 is exactly 7 in this case. So your RMS voltage is 7. So it's interesting. The average voltage is 4.9, but your RMS voltage will be then 7 volts. So that is difference between these two parameters. Now the RMS load current is now also straightforward to calculate because we have done a lot of work here in the first part in the question C. So we can say the RMS load current will be the RMS load voltage over the resistor. In this case, pure resistive. So we can just say 7 over 100, that will be then 70 milliamps. Okay, that's for the calculation here. Let's bring the results here and see that also in the simulations. Now we go to the simulation in MATLAB and Simulink. You see this is our voltage source we apply. This is a pulse. And this is the resistor 100. So we measure here the current. We measure the voltage here. We also measure actually the voltage here for the source. We apply everything to the scope. So I will show you that later in the next slide. But what you have already here, that the average load current, RMS load current, average load voltage and RMS load voltage. So let's go one by one. The first one is average load voltage, because that was the first question. That's 4.9, which is also what we had. The second one is the RMS load current, which is 0.04899, so very close to what we have calculated. The other one is 7 volts for our RMS load voltage, and also same, that is now here 0.07 RMS load current, which is then 70 milliamps. So that's all checked. Let's see what the waveform is actually for this case. Now in this case the source is given by this pink color. You see that actually it's 10 volts and then it jumps down to 0. But the shape will be the same for the load voltage and also the load current, because this is a linear load, so it won't change the shape at all. So this is the V out and this is the I out. Okay, that's for the first example. This is pretty straightforward, so we'll now build up the level in the next example. You see now here that we have a non-sinusoidal periodic source with different frequencies, and still we have a resistive load of 100 ohm. Again, we will ask the same 4 questions, but now let's look at the source expression. We have a DC quantity, 4, that is this DC, and we have 2 sine forms, so we have 8 times sine 400 pi t plus 10 degrees, and the other one is plus 5 sine 800 pi t plus 50 degrees. You see that the frequencies are different, so that is important to notice. We will do in the next example that we have the same frequency, and then we will need to look at that problem in a different form. You see here the VDC, that's again this one. The VS1 is this first part, and the VS2 is the second part. So we have actually 3 parts here in series, which will then make that VS. So let's see how we can determine the 4 unknowns here. The average voltage, again, that is really in this case straightforward. You just look at the constant value in this case, because that is 4. So you say the VO will be the VDC, so the DC term of your input, because that's just across the elements again of this resistor. That will be just 4 volts, so really done in 1 second. The average load current is again using Ohm's law, because we know from question A that it is 4. You divide by the 100, you get now 40 milliamps. Okay. Next one is the RMS load voltage. That is more work, so that is the square root of the summation of the squares of the load voltage, average load voltage, plus the RMS part of the first sine wave, plus the RMS type of second sine wave. So we have actually here the DC quantities and then the harmonics, let's say. Okay, let's see one by one what we have. VO, average load voltage, is 4 volts, we just determined in question A. VO1 is the amplitude of this sine wave, which is 8. Now we need to go to the RMS. Since this is a pure sine wave, we can just divide by square root of 2. That is a really famous formula. So you get an 8 over the square root of 2. This is now the exact expression of the RMS value we just need to substitute in here. Let's do the other one, VO2, which is the amplitude here, which is 5, and then going on here will be then 5 over the square root of 2. So in the similar form. Now we have the ingredients for this. 4 here, 8 over square root of 2, and 5 over square root of 2 here. That's shown here. Now we now calculate this. you get now 7.778 volts. So let's say 7.8 volts approximately. Now we have done now the RMS voltage part. Now the RMS load current. Again, this is really straightforward again because using Ohm's law, because we have done the major part of the calculation here. Now that's then 7.778 ohm volts, divided by the 100, you will get now 77.78 milliamps. Okay, good. Now let's now collect the values we have determined and now look at the simulation results in Simulink. Again, we have these sources. You see the AC voltage 1, AC voltage source 2, and also the DC, which is 4. This is just the summation from this expression. 100 ohms for our load. Again, we measure the current here using this ammeter, the volts across this load, and also the we measure the volts at this node from the source. That will go all to the scope. We will see that shortly in the next slide. Now let's go one by one what we have and what we now see in our simulations. The first one is the average load voltage, which is 4, so exactly as we have, because that goes from load voltage here. You see that, you take the mean, which is the average, you get a 4. The next one is the average load current from here. So load current, you take it out and you take the mean. That will be then 0.04 or 40 milliamps. So again, that is verified. The next one is the RMS load current. So you take from the load voltage, you make the RMS in Simulink, and you get now 7.778 volts exactly, actually, as we have. The next one is then the RMS load current, again from here, using the RMS continuous RMS block in Simulink, you get the value here as we have calculated. So that's all checked. Now let's see now the figure, so the plots for this situation. Again, you see here that this is a summation of three parts, which is a DC, and then 2 sine parts. That's actually this one, Vs. The green is our load voltage, which has exact same shape, of course, because that's just a parallel. And now we have also the exact same for the current. Again, that is of course a different unit, but you don't see any distortion. So it is not a non-linear load. So it is a linear load. That's why we have exact same shape for the input and for the outputs. Okay. Let's go to the example number 3 about, again, the same situation. You see, non-sinusoidal periodic source, but now we have same frequencies for this AC parts. And still we have resistive load. So we make only one change, which is going from the 2 different frequencies to the same frequency. So we had before 400 pi and here 800 pi in radians per second. Now we have 400 pi and 400 pi. Now what do we do now? Can we just say take these 2 independently and then move on? No, that's not possible. We will see why that's not possible, because we have the same frequencies and that will be then together one effective sine. So first, again, the calculations, so the VO, the average load voltage, that's really, again, the VDC, so I go a little bit faster, which is just 4, and an average load current, which is, again, using Ohm's law, which is then 40 milliamps. So this is exact same as in example number 2. RMS load voltage, that will be now different. Now we have now the DC part and also the AC part, which is then taking as the RMS. Now the DC part, we already know, that is just 4 volts. But what is now the AC part? Okay, that is more work, 4 volts. And the AC part, that is the question mark here. Now we need to use phasors and complex numbers to transform these 2 sine expressions into one sine expression. You can of course use trigonometry and etc., all those formulas if you prefer, it doesn't matter. So the end result is the same. Let's go one by one. Vs1 is this, and Vs1 can be also expressed like that, because we need to go officially to this cosine expression. So we need to go from sine to cosine. So we need to make in the cosine to minus 90 degrees to compensate for the sine expression, and then that will be then 8 times cosine of 400 pi t minus 80 degrees effectively here. And now if you now convert this to the phasor notation, it's really straightforward. You take the amplitude and there's the phase, which is then amplitude is 8 and the phase is minus 80 degrees, and then you of course place also the unit here, and you make now the capital letter from the small letter here. That means that you go from the time domain to the frequency domain, because you can also go from the phasor notation to the rectangular expression, which makes then this amplitude 8 times the cosine of this phase plus j times the sine of this phase. I have discussed this in great detail in other examples about phasors and complex numbers, so you can see that in another video on my channel. So this is really straightforward, I assume. And you can now also calculate now this using your calculator, what now the cosine of minus 80 degrees is, that's just this one, and the sine of minus 80 degrees, that's this one approximately. And you take and also work out this parentheses, you get now this expression. In a similar form for the second part, so we have now here 5 sine 400 pi t plus 50 degrees, you see that here. And in a similar form, so I go first to the cosine form by subtracting here minus 90 degrees. Now make it that simplified here, and then go to the phasor form, and then also now again go to the rectangular form by taking the cosine of this angle and also plus j and the sine of that angle, and work it out using your calculator, and also work out this parentheses, you get now this expression. Now we have the Vs1 in the rectangular form and Vs2 in a rectangular form using complex numbers. Now we need to add them up. Now you have it in the rectangular form, so you can add them up very easily. So we can say combine the expressions. So with the AC part is just Vs1 and Vs2 together. So that is this part plus this part. You see that here? Now you need to bring the real parts and the imaginary parts together. So you need to add the, let's say, the apples and the bananas separately. So we have now here the real part here, a real part here, imaginary part here, imaginary part here, and effectively then this, so 5.219 from these two values, and minus j 11.09 from these two. You can do that for yourself, it's really straightforward. Okay, and then what? Now then we need to determine here what our expression is in the amplitude and also the phase. Now the amplitude here from this is, you take the square root of the real part squared plus the imaginary part squared. That's shown here. And the phase is always the imaginary part divided by the real part. That's also shown here. Now, arctangent of that expression. Now when you do that, you will get now 12.26, and then the phase is approximately minus 64.8 degrees. Now what do we have now? What do we have achieved now in this complete analysis here? Now we know now what our amplitude of the AC voltage is, which is now here 12.26. So we can say the following. Our AC voltage in time domain is also given by this expression. Again, the same frequency. So you could again do that, this combination of the two sine terms using trigonometry. But now we have done that using the phasors and complex numbers, so you see that here. Now we need to add them up. We know that the full input voltage, the source voltage, will be the DC part plus the AC part. Now the DC part is just 4, now the AC part is here. That is actually what we just determined. So we go now from the phasors to time domain, and now we have it here. Now if you now look at this expression, we can directly calculate now the RMS load voltage, because RMS load voltage is then equal to the RMS source voltage, and that will be then the 4 squared plus the amplitude here divided by the square root of 2, again because it is a pure sine wave, and quantity squared, and that will give us 9.547 volts. Okay, you see that the calculation in this case compared to example number 2 is more work, because you need to convert these two sine forms to one sine form. The next one is the RMS load current, which is now really straightforward because we know Ohm's law. That's always helpful. We know the RMS load voltage divided by the resistor. Just divide this divided by the 100, and you will get now here 95.47 milliamps. So that is now the result here. Now let's bring them all together. That's these are the values we just determined, the summary, and we will now look at the Simulink, again the same format, but now two different, two same frequencies, again the same load, straightforward discussion as before in example number 2. I go one by one. You see here the average load voltage 4 as before. You see the average load current 0.04 or 40 milliamps as before. This one is 9.579, let me repeat, 9.547 volts. That is for this one. And the other one is here 0.09547, which is then also what we have calculated. So we can say this all checked. And let's also see the waveforms. That's also helpful. You see indeed that this is just a level shifted version of a sine wave, because if this were two different frequencies, you have seen that in the example number 2, there was actually a different shape. Now we have a pure sine wave. So you can see there's a periodic waveform, and it is shifted just by 4 volts compared to that combination of these two sine waves. So everything is actually the same. There is no non-linearity here. So the source and the output and current and the voltage are exact same shape. Only the value here for the load current is different, of course. Okay, let's now go to the example number 4, which is a bit more interesting, because again we have two different frequencies, but now we have an RL load. So we have a series resistive and an inductor. So in this case 5 ohms and 15 millihenries. The expression for the source is shown here. Again, we have some calculations to do. In addition, we need to also know what the absorbed power is by the load. That is also interesting. Okay, let's go for the calculation. Average load voltage. Again, straightforward, because we only look at the DC part, which is 10 volts. And since at DC the inductor is a short, you can also look at the reactance of an inductor, because that is at omega is 0, which is a short. The only thing that matters is the resistor, so you only see the resistor here, and that means we have here the 10 volts. That's just here. Okay, the average load current is again using Ohm's law, so 10 over 5 is 2 amps, again as said before, because the reactance of the inductor is 0 at 0 radians per second, or 0 hertz. So that's actually question A and B very fast. Now question C, that's the RMS load voltage. Again, that's the summation of these squared parts in the square root. And we know that we have the average load voltage of 10, and now we need to find these two parameters. Now you look at the 10, 20 and 30. Can we do that right away? Yes, because these are two different frequencies. Now we know that VO was the load voltage, average load was 10 volts. And VO1 is 20, looking at that one as amplitude. Now you go to the RMS, you divide just by square root of 2. And the other one is you take the 30 and you divide by the square root of 2, and you get out these two values. Okay, now having calculated the elements here, we can just substitute them. 10 squared plus 20 over square root of 2 quantity squared, and then 30 over square root of 2 quantity squared. That's all from here. Now that will give us 27.39 volts. Okay, that's for question C. Now the D, that is the RMS load current. Now the RL load is given by, because now we have an RL load, it's not just resistive, so we have an impedance. That is then given by this, which is a Z is equal to R plus J omega L. Now I have also put here a subscript N, because we have two AC parts, so we have to treat them separately. We also have AC terms of the load voltage are given by this expression, so we can say now VO1 and VO2, so we can designate that like that. And we have also the AC terms of the load current that is related to that load we have, and also the AC terms of the voltage. That is just using Ohm's law. That's this. Okay, this is in general what we need. Now what we have, now for the first one, the load part for the current is you take the first sine wave, or cosine in this case, divided by the impedance caused by this first frequency. You see that actually, because this VO1 here, VO1 is 20, because that's the amplitude, and the angle is minus 25, because we have everything in a cosine form. And that will be divided by the impedance 1, because N is 1, and the resistor is 5, and the plus J omega 1 will be 120 pi, you see that here, and times the L, which was 15 millihenry, or 0.015. So that's all shown here. And the next step is, in order to calculate this, we need to have the Z1 also in the phasor notation as we have in the VO1. So you go to this expression, so you can just simplify this. It makes 1.8 pi. Now we need to convert this to a magnitude and an angle. That is actually what we have seen in the phasor calculations. So that will be given like this. So we have now here the magnitude and the angle. Now you divide by 20 over 7.55 and also do the angles. So you do minus 25 minus 48.5. So you divide the magnitudes, you subtract the angles, and the effect is shown here. And this is now the first part of the current due to that first frequency. In a similar form, so VO2 is IO2 is then VO2 over Z2. Now that's shown here. You see the frequency is now 240 pi, so it has changed. In a similar form, you go to the phasor notation for our denominator and then use this, and you have now an expression for your current also for the second frequency. What do we do next? Now we have now the necessary information. Now the RMS load current will be then the summation of the squared part of the load, average load current, and the part what we have determined. So IO1 and IO2, all of them in RMS format squared. So moving on, and then substitute the values we have now determined. We get this. So see the 2 squared from the average load current. The amplitude here divided by the square root of 2, because this is a pure sine wave. And then quantity squared in a similar form for the second one. And that will give us 3.231 amps. Okay. The absorbed power by the load is really due to the resistor only. So we have that absorbed load power. That will be then IORMS, which is determined, squared quantity times R. So this is just the familiar I squared R formula. We know it is 5, the resistor as 5 ohms. We already have that from the IORMS also. You calculate it, you get now here 52.2 watts. So again, look at the units. This is the true power or real power, and it's not the reactive power. So that is not what we have in the inductor. Okay, now let's also look at the simulations, because this is what we have determined. This is the circuit. You see now here the series combination of the resistor and inductor. Now let's also look at the result one by one. 10 volts average load voltage as we have, 2 amps average load current as we have, the RMS load voltage as we have determined, and also the RMS load current is very close to what we have, a small difference. Okay, that's checked. Let's also look at the waveform. Now we have the shape here. This is now the input from this VS. So that is VS, but the load voltage will be again exact same shape. So that doesn't change, the green one, but the current is different. You see that also because that's just a phase shift, etc. But it is not a distorted version. It is just a phase shifted version. Okay. That's for example number 4. Now going to the example number 5, which is, let's say, one of the complete examples where we have a lot of stuff here. Let's say we have an R and an inductor and also the DC voltage source here. So the load is now a series combination of the resistor, inductor and a source. Similar form for the source, we have now again the 3 parts, DC part and 2 cosine AC parts. Again, we need to calculate 5 things here. So let's go to the calculations. Average load voltage, again, really straightforward. You look at the VA, that is our DC voltage we apply. That is what we measure, that is then 50 volts. It is not that we measure this one, it is really this. Average load current is, in this case, you need to be careful because you already have the VB here, which is 12. It's not minus 12, by the way, it's just 12. So you do VA minus VB divided by the R, which is 4, so you get now 9.5 amps. Okay, the RMS load voltage, again, the same expression. We need to look at the load voltage in the average form and also the AC terms. We see that here. Now, we know that these are 2 different frequencies, so we can just take them separately. Now, this is 50, so we can take that. The other one is 30, divided by the square root of 2. You get now this. Next one is the VO2, which is 10, and you divide again that by square root of 2 because it's a pure sine or cosine form. And you have now this RMS value. Now you substitute now the values in here. You get now this expression that will give us 54.77 volts. The RMS load current is against using the impedance form from this load. We have now the RL load, which is given by this impedance, which is our R plus the J omega N L. Again, we need to look at the separate frequencies. So we have two different frequencies. We also the AC term of the load voltage are given by this expression. And we have also the AC term of the load current, which is using Ohm's law by this expression. So we need to go one by one. Now the first one, which is IO1, is equal to VO1 over Z1. This 1 really refers to the first frequency, which is here in this case 240 pi. In this case I start with 30, and then the angle is 0 degrees because there is no angle here in the parentheses for the cosine. And now we have 4 here, and plus J 240 pi times 0.010, which is our 10 millihenries. Again, convert that to the phasors notation. First you simplify and you make this, so you have an angle and also the magnitude. Now you do 30 over 8.54, that will give us 3.51, and also the angle will be here shown. In a similar form for the IO2, you take now the 10, and also the angle is 0 degrees, but now you have 480 pi, and again similar calculation, you have the exact same inductor. You just substitute the values here and you simplify this, and you go to the phasor. You have now this current 0.641. Now we have the AC terms. In order to calculate now the load current, RMS load current, then the RMS load current will be then given by this expression. Again, the average load current squared quantity plus the AC terms each squared for the RMS. That means you need to divide this by square root of 2 and also this by square root of 2 and then square the quantities. That's all shown here. And that will give us 9.83, which see here is beside the calculations that actually the RMS load current is close to the average load current. So the harmonics or the AC terms doesn't do much actually in this case, so little effect. Okay, the final one is absorbed load power by each element in this case, so each load element. So we need to look at the R, we need to look at the inductor L, and also the battery or the DC voltage source here VB. Let's go one by one. The first, the inductor. The inductor will not absorb any effective power, so it means that PL will be 0. Why? Now let's bring this statement here. For a periodic inductor current, which is the case because this is periodic, the stored energy at the beginning of that period, of one period, is the same as at the end. So there is no net energy transfer. That means since there is no net energy transfer, indicates that there is no average power absorbed by an inductor. So at steady state we have 0 absorbed power by the inductor. It's also the same for the capacitor. Now for a resistor we already know that from the previous example, so it is now IO RMS squared times R, and we know what our RMS current is. We just substitute that here and also square that and then times 4, you get now this 387 watts approximately. For the DC source, we look at the average load current and also the value of this battery. Now we look at the PB, which is then the VB times IO. Now that's 12 times, because this is 12, times 9.5. So don't use here the RMS value of the current, because that is not really related to that DC voltage source. That is really the average current or the DC current. And that will give us 114 watts. Okay, now we have everything. Let's collect them together here and then go to the simulation results. This is now the circuit in the Simulink. Let's go one by one. Average load current 50 watts shown here. Average load current 9.5 amps. The RMS load current 54.77. also verified, and also 9.83 here. So everything is checked. Let's also see the plots. So this is now the source. You see here the waveform in pink. This is now the output voltage. You see here that in green, and the this load current is actually shown. It's interesting in the inductor current is it's actually building up and then stays at that value. That is the yellow one. So this is the final example of this series examples about basic power calculations which you encounter in power electronics. If you have any questions, comments about these set of examples, please let me know. I will try to answer them as soon as possible. See you next time in another video.